temperature increases by delta T, the length also will change. The change in length is given by delta L, as we all know. We can observe the negligible amount of expansion as the temperature increases. So if we square that negligible amount, we will get much more simple value, and hence we are neglecting this term. Coefficient of linear expansion, that is alpha L is equal to delta L by L into delta T. So from this we can write the change in length is alpha L into delta T. Hello everyone, welcome to session 2 of chapter 11, Thermal Properties of Matter. This is Swati from Department of Physics, Vidyashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in the last session we had studied about the properties of matter, and also we have studied about the basic concepts of heat and temperature. How does the matter behave when it gets heated? In which we have discussed about the thermal expansion and the types of expansion in solids such as linear expansion, area expansion and volume expansion. So in today's session, now let us derive the relation between a coefficient of linear expansion and the area expansion. So, the coefficient of linear expansion is given by alpha L and coefficient of area expansion is given by alpha A. Now, we are going to derive the relation between these two, how they are related with each other. That is, alpha A is twice the linear expansion coefficient, or we can also represent this alpha A as beta. So, beta is equal to 2 into alpha L is what we have to prove now. So, to prove this, I will consider a solid substance of length L. So, let L be the length of a substance or length of the object. Then its area is given by L square. Now, when the temperature increases by delta T, the length also will change. The change in length is given by delta L, as we all know. Now, the new length becomes, I will consider new length as L dash, which is equal to L plus delta L. That is the original length plus change in length as the temperature increases. So, when length changes, we all know that the object will expand by lengthwise, and also its breadth will get expanded, which means the area of the object will get changed because of the expansion in solids. Now, new area is given by A dash is equal to, I will consider it as A dash is equal to A plus delta A. But we know that from coefficient of linear expansion, we know the relation delta L by L into delta T. So, what is this delta L? That is change in length. So, delta L is equal to, multiplying these two, we will get alpha L into delta T. So, why am I writing the expression for delta L? Because to substitute in the new length. Similarly, we have new area as well. So, from coefficient of area expansion, I can write delta A is equal to alpha A into delta T. Now, let us substitute these two in equation 1 and 2. So, what do we get? We get L dash is equal to L plus, in the place of delta L, I have to substitute this value, that is alpha L into delta T. Similarly, the new area A dash is equal to, it was A plus delta A, so delta A is replaced by this term. So, that is A plus alpha A into delta T. But observe here carefully, a area, that is A is equal to L square. So, now A is equal to L square, or A dash is equal to L dash square. That is a new area after the expansion, which is equal to L dash square. So, what is L dash? It is L plus alpha L into delta T, the whole square. So, it is of the form A plus B the whole square. We know A plus B the whole square is A square plus 2AB plus B square. So, let us also substitute this in the form of A plus B the whole square. So, expanding this in the form of A plus B the whole square, we get A square, that is L square, plus 2 into A into B, that is L into alpha L into delta T. This entire term becomes B and this term is A. So, now plus b square we have. So, b square is alpha L square into L square into delta t. So, this is the expression after the expansion of the above expression in the form of a plus b the whole square. Now, the coefficient of linear expansion value is very small. So, we can observe the negligible amount of expansion as the temperature increases. So, if we square that negligible amount, we will get much more simple value, and hence we are neglecting this term and we are writing L square plus 2 into L square into alpha L into delta t. So, L square is nothing but length square, that is area, plus 2 into alpha L I can write, and L square is again area into delta t. So, I will call this as equation 3 and this as equation 4. Now, observe equation 3 and equation 4. So, we have new area A dash, that is A. In the place of A we have A itself, and here we have alpha A. So, here in this expression we have 2 into alpha L, and rest of the terms are same. So, from these two equations we can write that alpha A is equal to 2 times alpha L. Is the relation between coefficient of area expansion and coefficient of linear expansion. So, this expression can also be written as beta is equal to 2 into alpha L, where beta is nothing but the coefficient of area expansion. Similarly, the relation between coefficient of linear expansion, that is alpha L, and the coefficient of volume expansion is given by volume expansion coefficient is 3 times the coefficient of linear expansion. So, let us derive this now. So, we know from coefficient of linear expansion, that is alpha L is equal to delta L by L into delta t. So, from this we can write the change in length is alpha L into delta t, as well as from volume expansion coefficient it is delta V by V into delta t, or we can write this as delta V is equal to alpha V into delta t. Here also I have considered a substance whose length is L. So, the new length is given by L dash, which is nothing but L plus delta L. What is L? It is the original length, and delta L is the change in length. So, to substitute here, we must know about delta L and delta V, and hence I have written it earlier. And next, if the length of the object changes, we all know that the volume also will get expand. So, the new volume is given by V dash is equal to V plus delta V. We know length, cube of the length is nothing but the volume. So, the new volume V dash is nothing but L dash cube. So, what is L dash? L dash is L plus delta L the whole cube. So, let us now substitute delta value here, and we get L plus delta L is nothing but alpha L into delta t the whole cube. Now, this is of the form a plus b the whole cube. So, what is the formula for a plus b the whole cube? That is a cube plus 3a square b plus 3ab square plus b cube. So, now let us simplify the above data in this form. So, we will get a cube, that is L cube, plus that is alpha L into delta t the whole cube, plus 3a square b. A is nothing but L. So, 3L square. B value is nothing but alpha L into delta t plus 3ab square. So, 3 into A is L and B square is alpha L into delta t the whole square. So, expanding this, we get L cube plus alpha L cube into delta t plus 3L square alpha L into delta t plus 3 into alpha L square into delta t into L, because it is 3ab square. So, now as I explained in the previous derivation, alpha L value is very negligible. So, the higher the value like alpha L square and alpha L cube, we will get much more smaller values, and hence we will neglect this in the above expression and we will retain the other terms. So, here L cube as it is I am writing plus, and in this term we have 3 into L square we have here. So, L square into L is L cube alpha L into delta t. So, here L cube is nothing but the volume plus 3 into alpha L into L cube is nothing but the volume into delta T. So now look at this equation. We have change in volume, that is V dash is equal to V plus delta V, that is V plus delta V is given by alpha V into delta T. Now compare this equation with the arrived equation. Here also we have V plus 3 into alpha L into V into delta T, and here also we have alpha V into delta V. So comparing these two equations, in the place of V here we also have V, and in the place of alpha V we have 3 into alpha L. So alpha V is equal to 3 into alpha L. By these two equations we can conclude, and this is the relation between the coefficient of volume expansion and the coefficient of linear expansion. So from this we can say that the coefficient of volume expansion is 3 times the coefficient of linear expansion as the temperature increases. So this is all about the expansion in solids. Like solids, even the liquids and gases undergoes expansion as the temperature increases. So now our next topic is thermal expansion in liquids. So liquids also expand much more than solids when heated, and liquids do not have a definite size or shape, but it has a definite volume. So therefore liquids have only the cubical expansion. So cubical expansion is nothing but the liquid also undergoes expansion. Most of the liquids will undergo expansion when they get heated, but a special property or a special liquid, that is nothing but the universal solvent, that is our water, it has got a special property that they never undergo expansion as soon as they get heated, but it undergoes contraction until 4 degree Celsius. So after 4 degree Celsius, the water also will expand, and this special property is called as anomalous expansion of water. Anomalous expansion of water is nothing but the special property of water. Why it is called as anomalous expansion? Because if water is cooled below 4 degrees Celsius, its volume increases and its density decreases. We all know that the density is inversely proportional to volume. Whenever the volume is more, density will be less, and vice versa. So water has maximum density at 4 degrees Celsius. You can look at the diagram. At 4 degrees Celsius, till 4 degrees Celsius, water will get contract, and after 4 degrees Celsius, it will expand. But the other liquids will undergo expansion as they gets heated. So at 4 degrees Celsius, you can observe the volume is very less. When the volume is less, the density will be more. So water has a maximum density at 4 degrees Celsius, and this property is known as anomalous expansion of water. Here in this graph, we are showing the variation of volume of water with respect to temperature. As I explained, the volume is minimum at this point, that is at 4 degree Celsius. When it is minimum, the density of the water will be more. And the density versus temperature graph is shown here. So density at 4 degrees Celsius is more as its volume is less. So this special property of water is called as anomalous expansion of water. So what is the advantage of this anomalous expansion? Due to anomalous expansion, water on the surface of lakes and ponds, they freeze at the top layer first, and hence it will not affect the living creature which is living inside the water, which means the marine animals or the aquatic animals can live happily even though the surface of the water is freezed. So this is about the expansion in liquids. By taking an example of water, we have studied the special property. So expansion in solids is discussed, and expansion in liquids also we have discussed. Next comes the thermal expansion in gases. So gases will also expand when they are heated. Gases compared to solids and liquids, they expand more and they expand to a larger extent. Like liquids, gases do not have a definite shape, so they also have only a cubical expansion. Today's session, we have learnt about the expansion in liquids and gases, and also the relation between the coefficient of linear expansion and area expansion, and the coefficient of linear expansion and volume expansion. In the upcoming session, we will learn more interesting concepts about thermal properties of matter. Until then, keep learning, all of you. Thank you.